And I'm happy to introduce Tamlin Pavelsky. He got his PhD in 2008, and he's now a professor at the University of North Carolina, United States. He is especially interested in global hydrology, particularly understanding global characteristics via satellite remote sensing. He works on scales from the entire globe to individual single wetlands. Especially interested in the Arctic, subarctic systems. And this is also reflected in the title of today, which is From Secchi Disks to Satellite. And we had a chat, and I confirmed that he does own more than one Secchi disk. So a few things about Tamlin. He mentioned that it's a coincidence. SIL now turns 100 years. Tamlin just had his 100th paper published. He is a leader of something called SWOT, which is the Surface Water and Ocean Topography satellite mission. It will be launched at the end of this year by the NASA. He got a Presidential Early Career Award for Scientists and Engineers, and that is the really highest U.S. government award for an early career scientist. That was in 2012. So I asked you, is there anything special I should mention? And then you said, I am citing you. What I am probably most proud of professionally are the students and postdocs who have come through my research group. That's good. And many of them, several of them are already in successful careers, being professor or having other really good jobs. And finally, it might be interesting to know that Tamlin, he grew up outside of Fairbanks, Alaska, in cabins away from running water and away from electricity. So he's an experienced hiker and canoeer, I guess. So welcome, Tamlin.
Hello, everyone. Thank you so much for being here today, and I'd really like to thank the committee for inviting me. This is my first SIL meeting, and it's really been enjoyable. I particularly enjoyed the opening plenary session, just really diverse talks. And it's amazing, 100 years, right? That's an impressive legacy. But I think it was also interesting to be reminded that 2022 isn't just the SIL anniversary, it's also the anniversary of other important things. So, for example, Ambassador Torresen reminded us that 50 years ago we had the first meeting on global environmental cooperation in Stockholm in 1972. And 1972 actually was a kind of a revolutionary year in a lot of ways, right? So I looked it up, and it was actually the first year that handheld calculators were available, at least scientific calculators. And it was the first year that ABBA music was released. But perhaps more pertinently for us, and I probably need this, it was actually the first year that we had an Earth-observing satellite. So in 1972, Landsat 1 was launched. And now we kind of take for granted that we have all of these Earth-observing satellites up there. But in the late 1960s and early 1970s, it was actually really a heavy lift to get this launched. So Virginia Norwood was an engineer at NASA who was really the person behind Landsat. It's amazing what she designed and what her legacy is. And she had a tremendously hard time convincing people that we needed to have a multispectral imaging satellite up there. And it was only when the U.S. Geological Survey came on board as a partner to NASA that we could actually get this, well, when I say we, that she could actually manage to get this launched. And so, it was really 50 years of Landsat, right? Really this sort of amazing advance. And as the name Landsat implies, right, the satellite wasn't really intended for inland waters, right? It wasn't river sat or water sat or something like that. But if the history of remote sensing of limnology is anything, it's all about taking satellite data that weren't originally intended for us and figuring out how to use them. And so this started very quickly. So I've found some sort of other slightly earlier papers that are in more obscure publications. But the earliest sort of really solid publication that I've found is from 1976 by Jerry Ritchie and colleagues. And essentially what they did is in some reservoirs in Mississippi in the United States, they went out and they measured total suspended solids, which is on the y-axis here. And they looked at whether there was a relationship with reflectance in various spectral bands. And they found that in all four of the Landsat 1 bands, there was a nice relationship, especially in the red and near infrared parts of the spectrum. And so we were off, right? We could actually measure limnologically relevant variables from space. And really, of course, that was only the start. So a few years ago, one of my graduate students led a review paper on sort of the history of science in water quality remote sensing. And this is a figure, one of the key figures from it, and it shows the number of papers focused on different parts of inland waters that have been published in various years from the early 1970s to well, near the present. Since this was published in 2019, we have a few more years now. And you can see this just tremendous acceleration, especially starting in the 1990s or even really in the 2000s was when we saw this really steep acceleration. And we can talk about why that might be. But, of course, there's been an acceleration in scientific publishing overall. So we actually went and did the analysis. And the publishing rate for inland water remote sensing has increased by about 3 times faster than scientific publishing overall. So this really has been an exploding field. And I know that not all of us are remote sensing specialists here. And so I would encourage you, if you're interested in dipping your toe into the remote sensing waters, we actually wrote this paper with people who are not remote sensing experts in mind. So there are other review papers that are great out there. If you already understand all the remote sensing terminology and want to dig into the methods, those papers are available. But this one is for people who maybe study inland waters and want to learn a little bit more about how remote sensing has been used and can be used. So, we've had this real explosion in research. And so what is it that we can sense? And the classic answer here is these sort of 4 optically active water quality constituents. There are various names for them. But this is the classical answer. So we can get at chlorophyll concentrations, we can get at chromophoric dissolved organic matter, or if you're talking to a broader audience, color dissolved organic matter. Concentrations, we can get at suspended sediment concentrations, and then we can, of course, we're sensing the water itself, right? So this is sort of the classic answer, but there are also lots of other limnologically relevant variables that we can also sense. And so 3 of the most common ones are water color, right? Water clarity, so think Secchi disk depth or turbidity, whether a lake or a river is ice covered. And then I put et cetera here because as satellites have gotten more capable and our algorithms have gotten better, people have developed sort of clever ways of getting at other variables. And this is especially looking at some of the sort of ecological and biogeochemical aspects, right? So rather than just looking at chlorophyll, maybe we can break down, okay, what's actually in the water biologically or in terms of CDOM, like, what kinds of chemicals are actually in the water. So there are a lot of interesting things that we can do with remote sensing. And then we come to the question of how do we actually do these measurements? What methods do we use? So as in many aspects of science, at least the way I view this is a little bit of a contest or a struggle between the physicists and the statisticians, right? And so in this case, the physicists are using what we often call quasi-analytical algorithms. And so the idea here is that you're trying to actually model as well as you can how light is interacting with the media through which it's passing, right? And so that would be the atmosphere, it would be water, and it would be the things that are in those to media, right? So whether that's sediment or dust or whatever. Statisticians are essentially taking a bunch of on-the-ground measurements and saying, okay, let's create some kind of a relationship between those ground-based measurements that we care about and the reflectance. And historically, oftentimes, this was sort of local statistical relationships. More and more, this is machine learning, right? So which one of these is better? Which one of these is the better approach? And here I'm actually going to go back again to our opening presentation. I really loved that presidential talk that we had, going back to the philosophy of science. I had some philosophy of science classes as a geography student, right? We had to think about that back when I was in graduate school. And so I actually want to go back to our good friend William James and pragmatism here, right? And so, can your method accurately predict what we observe in the world? And if the answer is yes, then from my perspective, that's a pretty good method. But of course, we have an asterisk on accurately. And so what accurately means depends on the question that you're asking, right? Sometimes we don't need real high accuracy, and that's great. And sometimes, we need something to be really accurate, and we need to think a little bit more about the methods. So what I'm going to talk about today, the results that I'm going to present, are actually mostly using statistical approaches. But in presenting these, I've seen some amazing results from quasi-analytical algorithms here. And so my answer to this is that I think that we really advance things by both of these approaches moving forward and coming up with clever ways of combining them. Okay, so let's talk a little bit about some of the trends in water quality remote sensing research. So this is another figure from that review paper. And what we did is we looked at what each of the papers that's been published on this topic, what it's actually sort of focused on. And early on, perhaps unsurprisingly, we had a lot of papers that were focused on methods. And then we sort of had methods, but with sort of some kind of a pattern application, where maybe you applied that method to an image and sort of looked at what was going on in the image. And then we started to have papers that were sort of looking at trends over time, right? So maybe you would say, look over the course of a season or a few years, right, at what was going on with a particular constituent. And really, it's only in the last 15 years or so, leaving aside a little blip in the late 90s there, that we've started to have more and more, and when I say applied here, what I'm really talking about is scientific applications, right? So trying to address science questions using remote sensing. That's really come online sort of in the last 15 years or so. And so what are the kinds of questions, what are the characteristics of questions or environments where we can really successfully use remote sensing? And this is just a list that I came up with out of my head. There are probably other things that we want to think about. But I tend to think that if you're looking at a really large area, right? So let's say you want to answer a question or address a question that's continental in scale or global in scale, right? There probably aren't a lot of great ways to do that. In some cases, at least, using in situ data. In some cases, we can do it, but remote sensing can be really useful there. If you're working in remote environments where maybe you can get out there for a couple of weeks a year, but it's really expensive to do a bunch of work there long term. If you're interested in spatial patterns, right? So it's really hard to go out into a lake, for example, and really comprehensively sample the lake all at one time if you're looking at an algal bloom or something like that. But with satellite imagery, we can help. In general, I would say that if you need like the highest level of accuracy that our in situ instruments can provide, probably remote sensing might not be the optimal answer, because our algorithms so far, in general, don't provide quite that same level of accuracy. It also needs to be okay for your question that we have sort of relatively low temporal sampling. So if you're working on something that varies on timescales of minutes or hours, and anything longer than that is kind of useless, then it's going to be hard to use remote sensing, although that's maybe starting to change a little bit as we start to have these sort of big commercial constellations that are up there. And then I think the last thing here, when I say surface measurement's acceptable, right? So if you're measuring sort of light bouncing off of a water body, mostly in most cases what you're measuring, not always, but in most cases, you're measuring what's happening either at the surface or sort of in some kind of a zone that's relatively close to the surface, right? And so if what you're trying to look at really has a vertical component to it that's critical, and that you can't get by looking at what's happening at the surface, then it might be a little bit more challenging to use remote sensing. So I've sort of done a lot of thinking about this and tried to figure out, okay, what are some of the questions that we can address using remote sensing? And so what I want to do for the rest of the time that I'm with you today is I want to tell you about 3 different questions that my research group has tried to address. And then I want to talk a little bit about where I'm thinking the future might be going, at least one aspect of it. So these are 3 really simple questions, right? Are lakes getting clearer or more turbid? Are suspended sediment concentrations in rivers changing? And when and where are lakes characteristically ice-covered? So, I mean, it's not that we don't know anything about all of these, but if we want to think about them on continental or global scales, right, that's something that's been pretty challenging to do up to this point. But before I go and start talking about any of these, I really need to do some acknowledgments here, because I am but a professor, and the people who are really doing the work on this are all of the graduate students and postdocs who've been in my lab. So these 5 people have done most of the work that I'm going to show today, and so I definitely want to acknowledge them, and I'm immensely proud of who they are as scientists and the work that they're continuing to do. So, and I'm sure the donkey is lovely as well. Okay, so let's talk a little bit about lakes. And the first thing, if we're going to use a statistical approach, a machine learning approach in this case, to measuring something like lake clarities, we need some kind of a training data set. And there are a number of people who've developed these kinds of training data sets. We actually went and developed our own. And we call it Aquasat. It was published in 2019. You can go and download it if you'd like. Just send me an email or find me on Twitter if you can't find it easily. And essentially what we did is we took some really big ground-based water quality databases. So this would be Lagos NE, which I know a lot of you are probably familiar with, right? So this is a database of water quality parameters largely in the Northeast US. And then the National Water Quality Portal in the US, which sort of aggregates a bunch of government observations. And we matched those up to same-day satellite reflectance from Landsat 5, 7, and 8. And this was from 1984 to the present. So sort of when we started getting modern Landsat data in about 1984. And this somewhat crazy psychedelic figure was put together by Matt Ross, but I really like it. So all of the little dots that you see are the water quality data, on-the-ground water quality data. And then the bars that you can see moving across, those are Landsat overpasses, which for one satellite happen every 16 days. And every time you see one of those white dots flash, that's a matchup, where we have, at the same time, or at least on the same day, we have a Landsat observation, clear sky Landsat observation, so no clouds, and an in situ measurement. And in total, across all of these measurements, we have more than 600,000 same-day matchups. And so this is a powerful database that we can use to try to figure out algorithms for detecting the water quality parameters that we're interested in. And so in order to detect water clarity in lakes, what we did is we extracted from that database all of the observations, in this case of Secchi depth. Or, I think we just use Secchi depth for this. And that's actually almost half of the database. So we started out with something like 278,000 of these matchups. And we did some sensor corrections that I'm not going to go into today. There's a paper that Simon Topp published on this in 2021 that goes into how we did this in more detail, but making sure that all of those different sensors are actually measuring things that are sort of comparable. And then what we did is we took 80% of that data and used it as training data. And I'm not going to go into great detail about the algorithm that we used, but it's called a gradient boosting algorithm. And so essentially the idea here is it's sort of an iterative algorithm that essentially solves the problem once and then looks at the things that don't do well and tries to make those better and does that over and over again. And then you combine all of those different sort of models, and that's your final model. And then what we did is we actually did some spatiotemporal aggregation here. So we can look at individual lakes, but the data for individual lakes, as you'll see, it's good, but it's still a little bit on the noisy side. And since we're looking at, in this case, the whole US, and we focused on the US here, not because we're not interested in other parts of the world, but because that's where our training data is. And we wanted to be careful that we weren't applying training data from one part of the world to somewhere where it may or may not apply really well. And so what we used is actually, there's this national lake assessment. In the US, I think the first one was in 2007, 2012, 2017, and I actually haven't looked. I hope there's one going on in 2022. Maybe some of you know. But they divided up the US into these 9 different ecoregions. And so we did that too. And then what we did is we took our remaining 20% of our data, which is about 50,000 observations, and we used that for validation. And so if we look at the validation, up in the upper, let's see if I can make this work. In the upper left-hand corner here, this is sort of observation level data. So if we take sort of one observation of one lake, and there's definitely some scatter here. So the mean absolute error is about 3/4 of a meter here. But there's very little bias, which is encouraging, right? But if we go and we aggregate that further up to the sort of this ecoregion level in space, and then up to sort of an annual time scale, and in this case we're just looking at sort of May through September, because we want to avoid the ice-covered season and all of the problems that presents. We'll come back to ice later in the talk here. So if we do that aggregation, then we get substantially better, right? And so then we have a mean absolute error of about 25 centimeters, which is about 14%, and again, almost no bias. So we feel pretty good about this, right? And so if we look at what one of these time series looks like, this is just for the coastal plain region. Let's see here. This is just for the coastal plain region down here, and you can see that it matches up pretty well. So if we look at, right, before I get to that. So one of the things that the National Lake Assessment did, which was really useful for us, is they actually created this sort of statistically stratified sample of US lakes, where they were like, okay, this is sort of a representative sample. And so we took those about 1,000 lakes, and we used our algorithm to calculate a time series of clarity based on those lakes. Now, we also did a much larger sample of about 14,000 lakes. And it turns out that there's some minor differences between these two, but it turns out that they're actually really consistent with each other. So I'm just showing you the sort of NLA sample in this case. And so if we look at that aggregation, here are what those time series of sort of regional lake clarity look like over time. And I think this is pretty cool, right? We can see over time what the characteristic clarity is of lakes in different regions in different years. And there's a lot of interesting stuff that the paper goes into here, but mostly what I want to highlight is if you look at a lot of these, and it's probably most obvious in the Xeric West, but it's also obvious elsewhere, right? It looks like there's this sort of increase in clarity over time. And of course, we can test that statistically. So we did that, and it turns out that in 7 of these 9 ecoregions, we have this statistically significant increase in clarity. So overall, lakes in the US are getting clearer over time, which is really interesting, right? And it's a little bit hard to, without using remote sensing and that sort of consistent sampling, and also sort of the long, consistent time series to know whether this was true or not. So actually, one of the other things that we did in this paper is we also just sort of aggregated all of the in situ data that we had. And the trends are really quite different if we just use the in situ data, because our sampling tends to be in lakes that are larger and lakes that are more problematic. At least that's our hypothesis. So why is it that lakes are getting clearer, or at least where are lakes getting clearer? So at this point, we just have hypotheses that are sort of suggested by data. So there's a lot more work to do here. But these are 2, I think, really interesting figures or figure panels. So the one on the left shows the distribution of slopes of those trend lines based on lake size. And so what we can see is that basically if you look at the biggest lakes, so larger than 100 square kilometers, no trend. And as you get to smaller and smaller lakes, you have a larger and larger trend. So mostly, this is happening in small lakes, right? We're getting things clearer in small lakes. So the panel on the right here then is looking at actually population density. So are we looking at lakes that are in really highly populated areas or in wilderness areas? And it turns out that if you look at sort of low population density areas, there's not much of a trend. But if you look at the highest population density areas, that's where these trends really dominate. And so what we're seeing are trends that are in small lakes in highly populated areas. And actually, the other thing I didn't put on here is that these trends, these changes are mostly happening sort of in the 90s and sort of before 2000. So the hypothesis that we suggest in this paper, and we would love to figure out how to test this more robustly, is that this might be related to things like the Clean Water Act, which was passed sort of before, not long before that time, back in the 80s. And essentially, that focused mostly on sort of these point source pollution sources in relatively populated areas. And so we might expect that lakes in those areas would be most affected. But this is something that we're hoping to test more robustly. Okay, so that's our first question. Let's think then, moving from lakes to rivers, and think about suspended sediment concentration. So we can also look at what's going on with sort of some of these other optically active constituents. And we built a very similar model to what we did for lakes, so I'm not going to go into this in any great detail. We used Aquasat again for training, used the same train and validation split. We used extreme gradient boosting again, and developed a model to be able to do this. And so the first thing that we did is we just wanted to see what are the characteristic suspended sediment concentrations in U.S. rivers. And before that, I forgot that I wanted to show you the validation for the model that we ended up producing. So it looks like this. We think it's pretty good. Probably not ideal if you're trying to look at sort of image-to-image variation. So again, we do some spatial and temporal aggregation, right? We're aggregating things up to sort of the scale of a reach that's maybe 1 to 2 kilometers, and we're averaging things to the scale of a year here. But overall, we think that this is a useful model. And so if we look at long-term mean concentrations, it looks something like this. And this is perhaps not surprising. So the first thing that I see when I look at this is, the Rocky Mountains and things that are coming out of the Rocky Mountains. Certainly not everywhere, but especially sort of over in the Colorado, and then on the sort of in the west side of the Mississippi Basin. Coming off of the eastern slope of the Rocky Mountains, we've got some really high concentrations, and then in places like New England and the Pacific Northwest, it's a lot. It's generally a lot lower. So this is interesting. If we want to look in a little bit more detail, right? You can look at this already, and for example, in the Missouri River, which is, let's see, right here, right? We can really clearly see like some areas where we have the impact of reservoirs. Right? And so this is perhaps not surprising. But what I'm not sure I've seen before are long profiles that go down an entire river. So if we extract for every year what the profile of suspended sediment concentration is from near the headwaters all the way down to the mouth. And so that's what we did. And these are just examples for 6 rivers. And so what you have in each case is over on the right-hand side, you have the mouth of that river, and then on the left-hand side, you have the headwaters, or not quite the headwaters, right? Because Landsat imagery can't get up that far. And then what we're looking at, each of the colors is the profile for 1 year from 1984 to the present. And there are a few things that are interesting here, right? Again, we can clearly see those impacts of dams and reservoirs, but we can also see sediment concentrations recovering as we're looking downstream of those features, right? So I think that's pretty interesting. We can also see that there are some rivers where we have these sort of clear increases in suspended sediment concentration as we go downstream, right? So the Yellowstone, which is a relatively unimpacted river, you can see these nice increases in sediment concentration. Things are more complicated in some of the more heavily impacted rivers, right? So places like the Arkansas and the Colorado and the Columbia. But the other thing that we can see is looking over time. If I look at all of these, I see a lot of purple near the top, and I see a lot of sort of yellows and oranges near the bottoms of these plots. And so we can take these and look for each reach at whether there's a trend in suspended sediment concentration. And what we get here is that something more than a third of US river reaches that we looked at have decreasing trends in suspended sediment concentration. Only 2% are increasing. And so overall, we're seeing this decline in suspended sediment concentration. And this has been seen before using gauge data. And so this sort of confirms that observation, but it also expands to sort of a larger set of rivers, right? Not just to the sort of relatively limited number of places where we have sediment gauges. So I think that this is really interesting. And I do want to say that we're not the only people who are doing this kind of work. There's lots of other amazing work, and we actually saw this figure in one of the plenaries yesterday. It's from a paper by Evan Dethier and colleagues that just came out in Science earlier this year, where they use the same kind of data that we use, Landsat data, to look at trends over time at the mouths of, I think it's about 500 world rivers, and come to some really fascinating conclusions about how they're changing. I mean, I had no idea that at this point that they estimate the majority of sediment flowing from continents into the world's rivers is actually coming from South America, which is cool. Okay, so let's then move on to our last question here, which is, when are lakes characteristically ice-covered? And this is something that we've been able to answer at the scale of an individual lake for a long time, right? I mean, we have these incredible data sets, sometimes going back to like the 1400s for some lakes. But if we want to think about this globally, right, that's something that we can only really do with remote sensing. And so what we did is essentially we combined Landsat data with the HydroLakes database. And we didn't actually at first use the entire HydroLakes database because the processing demands were just too high for sort of a first pass here. So what we did is we took all of the lakes worldwide that are larger than 1 square kilometer, and that's on the order of 140,000. And we applied a new algorithm that we developed called SLIDE. We published this, earlier this year, in one of the IEEE journals, so you can go take a look at it if you want. Essentially, we did a bunch of sort of manual classification of where there were ice, or where there was ice, and what kind of ice was it? Was it sort of dark ice, or was it snow-covered or relatively bright ice? And this is one of the things that I really like. You know, I'm all for fancy machine learning algorithms, and in fact, we use machine learning here. But I'm a firm believer that sometimes the best algorithm is sort of an army of willing and enthusiastic undergrads. And so in this case, we hired an undergrad who did a whole lot of this classification and is a co-author on the paper. So basically, we did 1,100 sort of manual labels of these ice-covered and non-ice-covered polygons, and then we classified essentially whether lakes were ice-covered based on a machine learning algorithm that I'm not going to go into in more detail here. But just as a quick example, here's an example of one lake. And what we did here is, ideally, ultimately, we want to have like year-by-year ice cover phenology, and that's something that we're working on. We have an algorithm that works pretty well. It's just a really heavy lift to do this for all the lakes in the world. So what we started with is we said, well, why don't we just get a climatology? And yeah, we know that things are changing over the Landsat period, but it's probably still useful to use that 30, 35-year period and get an idea of when each lake is freezing and when it's thawing. So what we did is we took all of the Landsat data and we aggregated it into sort of one data set for each lake. And so each one of these plus signs that you can see here is one observation. And up at the top, we have when the lake is completely ice-covered, and at the bottom, we have when it's completely ice-free. And then we just used logistic regression to fit a curve to this data. And for simplicity, we just defined ice cover as when we crossed the 50% threshold. And here we've expanded out to 4 lakes. And so we can actually calculate an ice on date, and we can also calculate an ice off date. And I will say that sort of because of when these happen, the ice off date tends to be significantly more accurate than the ice on date, because ice on tends to happen when it's really dark in a lot of places. But we can still detect that ice on date. It's just, in some cases, a little less accurate. And so what we can do is we can use those data to calculate for all of these lakes sort of when they're freezing and when they're breaking up, and what their ice cover fraction is characteristically, right, on different days of the year. And one thing that I'll note is we made this animation before we did sort of a really basic temperature correction. So if you see some things flashing in the Amazon, for example, right, that's really easily removed because, if the temperature out is 25 degrees Celsius, we're pretty sure that lake isn't frozen. So if we aggregate all of these data, we come up with a plot that looks something like this. So this is the fraction and the area on any particular day of lakes in the world, or lake area in the world, that are ice covered. And I guess this shouldn't be surprising, right? But some of those fractions are really high. Some of those percentages are really high, right? But that's just because most of our lakes, right? Canada has more than half of all the lakes in the world. They're very proud to say, right? I love Canada too. So basically, for each of these lakes, right, we can calculate a characteristic ice on date and a characteristic ice off date. And so for ice on, it's amazing. Like this large fraction of the world's lakes have ice on in October. And ice off tends to happen sort of characteristically in May and June. And then we can calculate from those an ice duration, an ice cover duration, right? And it turns out that more than 70% of our lakes worldwide experience more than 6 months a year characteristically of ice cover. And only 7.8% of our lakes never freeze. So those of you who work in sort of ice-covered systems or are interested in like winter limnology should be like patting yourself on the back right now, right? It's like, yeah, my system's important, or at least common. So I think this is interesting. So just aggregating all of this, about 92% or more than 2% of our lakes experienced ice cover characteristically. More than 70% were frozen for more than half of the year. And mostly this is ice on in October and then ice off in either May or June. So these are some of the things that we can do with this sort of Landsat time series now. But there's a whole world of remote sensing out there that isn't Landsat, right? So I grabbed this from NASA. I could have done the same thing from Copernicus, or indeed sort of the global, someone should make a global sort of figure showing all of the Earth-observing satellites that we have. Maybe that exists, but I couldn't find it in my Google searching. So basically, if you look at all these satellites, and I'm not going to go through all of them, almost all of them measure something that's either directly or indirectly related to limnology. And so what we can do if we don't think about just one type of satellite, but we think more broadly, I think that's really where the future is going. And I want to tell you about just one satellite that's launching later this year that I'm deeply involved in. Lars mentioned it earlier, that I think is going to be a game changer for a totally different aspect of limnology. And that's the Surface Water and Ocean Topography mission. So SWOT's a radar satellite. It's not an optical satellite. And it's designed not to measure water quality constituents, but instead to measure water level. And at the same time, measure inundation extent. And it's designed to do that in rivers, in lakes, and in the ocean as well. So there's a whole set of sub-mesoscale oceanographers who work on this, and I'm not going to talk about that at all. It's a joint satellite between NASA and CNES, the French Space Agency, and the UK and Canada have also provided contributions, so go Canada. And so it's really an international collaboration. It's scheduled for launch in just a few months. So November, December, probably December at this point. And it's designed to measure kind of the same kind of rivers that we've been looking at with Landsat, right? So 50 to 100 meters wide and wider. And then it can measure lakes as small as about 1 hectare is our goal, about 6 hectares is our requirement, right? So this is going to be quite a lot of lakes and quite a lot of rivers. And so let's take a look at what that actually looks like. So this is a data set that my lab group created Elizabeth Altano led it, that shows all the rivers that we hope to observe with SWOT. And there's about 2.1 million kilometers of rivers here. And what we're showing in colors here is SWOT basically, its overpasses every 21 days for most of its life. But a lot of those places, especially as you get to higher latitudes, you sort of have crossovers between the sort of observing SWOTs. And so as you get to really high latitudes, where a lot of our lakes are, right, you can get 3, 4, 5, I think the largest number for any river that we've ever observed is 36 observations every 21 days. And so this is going to be really exciting. And I think it's going to be a game changer for rivers, but we do already have a global gauge network for rivers. But our global gauge network for lakes, I think, isn't nearly as good. And so I think for lakes, it's going to be maybe even more revolutionary. So we're going to be able to observe water level in something like 2 million to 6 million lakes worldwide, at least once, and hopefully in many cases more than once, every 21 days. And I think this is going to be amazing. And I think it's going to be even more amazing if we don't just think about this from the perspective of SWOT alone, but if we think about bringing in all the other satellite data that we have, right? So wouldn't it be cool, for example, if we could get CDOM concentration and water level variations in 2 million lakes worldwide, over a whole series of years? What kind of science could we do with that? I'm really excited to find out. So we're coming to the end of my talk here. Just a few final thoughts. I really think that the scope of limnologic remote sensing, it's just really rapidly expanding. We're seeing new algorithms, but we're also seeing new applications of those algorithms. I'm a big fan of these machine learning approaches. I think that they're, especially with these new really big training data sets, I think they're really promising. But I also think that the physics-based algorithms are really important, and they can do things that the machine learning algorithms can't. And so what I want to see is more cooperation there. And finally, as I just mentioned, I think these multi-satellite approaches where we're bringing in these different technologies and the in-situ data as well, right? Satellites are never going to replace in-situ measurements. I think that we can use those kinds of approaches to push the boundaries even further. So if I have time, and hopefully I do, I'd be happy to take any questions.
Thanks a lot. That was an amazing presentation. Yeah, questions? Anyone?
I think we have one over there.
Oh, there's one.
We have a couple.
Over here.
First of all, thanks for your talk. I think I was first, sorry. Just a short question. What is the future of the spatial resolution with new satellites?
Oh, that's a really good question. So certainly we're seeing higher spatial resolution from, I would say, I guess, governmental satellites, right? So Sentinel-2 has higher spatial resolution than Landsat. And the next iteration of Landsat is going to sort of move in that direction as well. But we also have these commercial satellites, right? So from companies like Planet, and then it's harder to get the data and more expensive, but places like Maxar, where we can get really high resolution. The problem is, let's say you have 1 meter resolution data every day for the world. How do you even analyze that, right? So I think there's this trade-off between like processing power and our ability to actually ingest that amount of data. So my question is, where and when do we really need that higher resolution? And let's go for those applications specifically and figure out how to do that.
Okay, there was one more, and then we have to change.
Yeah, maybe I missed it, but because you have pushed a lot of information here. But what will be the precision of this radar measuring the water level?
Yeah, that's a really good question. So the way I like to think about it is that the more you average, the more precise it'll get, because you're going to beat down a lot of this sort of radar noise. So the number that I like to quote is if you have a lake that's 1 square kilometer in area, you should have a precision of about 10 centimeters. So most of the time, probably good enough to be useful.
Mm-hmm.
Okay, thank you. If there are any further questions, you will find.
I'm here.
Find him. Thanks a lot. No, stay here. Stay here. We also have the secret